Hi, how's it going? My name is Carl Diaz with the Learning Resources Center here at the University of Colorado, Denver. Today we're going to be talking about the concepts associated with work. Now, work can come across as pretty straightforward because the math can feel straightforward, and when the math feels straightforward, you think you understand it, but trust me, it isn't that straightforward. So let's make sure we understand everything that's going on, okay? So first of all, you need to understand what the definition of work is, okay? Work is the transfer of energy to or from an object, okay? We could look at the total amount of energy that was transferred to and from an object, which is the net work, or we can look at the individual. This just means work individual, IND, and F, IND. I'm just being generic here, where this is work net and F net, right? So you can either find the net work or the total amount of transfer of energy to and from the object, or you can find what each individual force itself is doing. Is it transferring energy in? Is it transferring energy out? So there's two ways to write this equation, right? We have this general equation, but there's two ways to write it, either in terms of work net or individual forces, right? Now for work net, you can also net the work. There's a video for you to watch that shows how to net the work on a box on a ramp. So you know how to do that, but there is this very general way of knowing that the net work is equal to the net force times displacement, okay? Or the net force, or how far, right? You got to be able to read these equations. This equation's telling you something, right? It's telling us how far the force was applied, right? Here, it's how far the net force was applied. Here, it's how far the individual force was applied, right? We know that because that's what X is. It's displacement, right? And so when you know how long they were applied, we know how much energy they put into the object or took it out, right? Friction pulls energy out. Like a push puts energy into an object, right? So this is what we know, right? So when we look at the general equation, no matter which one we're looking at, it always stays true, right? The theta is going to be the angle between force and displacement, okay? So if it's 257, then it's 257, right? Whatever the angle is, all right? Typically, it's going to stay within these angles right here, but you might have one without it. So whatever the angle, whatever the angle between like if I have a cart that's being pulled by a horse, right? Well, here, right, there's an angle, right? Here's the force of tension, but displacement is this way. Oops. Right? Displacement's that way, but tension's at an angle, right? Do you see that? So here, the angle between tension and displacement is whatever that angle is, 30, right? But we could use the components of tension, right? The x component of tension, it aligns directly with displacement. So we could use the x component of tension and just say that there's no angle between them, right? So it depends on how we look at it, but if we're looking like this, that would be displacement. Tension's at an angle here, so it's that angle. That would be the angle between force and displacement. But typically it's different, so you want to make sure that you go watch the videos after this with the box on the ramp and stuff like this, because it's describing how to use this stuff. These are just the concepts. We want you to know how to use it, okay? So that theta will always be the angle between force and displacement, all right? Either just the individual force and displacement, or that angle can be between net force and displacement. That's what that's saying, right? It's the angle between the force or net force vector and displacement vector. It's the angle between them, right? And the thing that we know is that once we put that angle in there and get cosine of whatever that angle is, we're actually getting the sign for work. That's important. You have to know that because work is a scalar value. Since work's a scalar value, the sign of work isn't coming from the direction of the vectors. I'm going to say that again because you have to know this. The sign from work does not come from the sign of the vectors. It comes from cosine theta, okay? The sign for work means something different than the direction, all right? All right, in fact, we'll talk about it right here, what it means, but keep that in mind. It's super, super, super important. The sign for work doesn't come from vectors, and that's not supposed to be a sign for work. I'm just saying that's the general equation, right? But it comes from cosine theta, not from the vectors, not from the force vectors, not from the net force vector or that, right? It gets the sign for work, okay? The sign for work comes from cosine theta. All right, so in cosine, we need you to memorize this because we're not going to tell you this, but this is important stuff to remember, these angles. When cosine theta is 0, it's going to be a positive one, so that means that positive sign you'll just pull out outside of work. So what I do is, after I figure out cosine theta, I don't write cosine theta anymore. I just write force and displacement, but but then cosine theta gets replaced with the sign out here, right? So what I'm trying to say is that once I find cosine theta, I don't write it because it gets replaced either with a positive or a negative in front of the work, okay? You don't want them both. So that's what I do once I get that sign, is I'll write it out here. If it's positive, then I write a positive. If it's negative, then I write a negative, okay? So cosine theta 0 is positive 1, or force and displacement vector in the same direction, it's positive 1. Cosine 90, right, or if they sit perpendicular to each other, then cosine 90 is 0, and that means work is 0. If that's all 0, 0 times this is 0, right? And if for cosine 180, that means force and displacement vector are opposite directions. Force would be that way, displacement that way, opposite direction, typically with like friction or something like that. So negative 1. So if this cosine theta was 180, I would replace it with a negative. This cosine theta was 0, I'd replace it with a positive in front of work, okay? And then cosine 270 is equal to 0. So these are the typical angles, but not the only ones. Like I said, you could have any angle, all right? Okay, so what are the concepts that we really need to know and get to understand and make sure that we have in our heads? The first one is that we get a positive work, that sign, that positive work, we're transferring energy to the object. The next thing we need to know is when we get a negative work, we're transferring energy from the object, okay? And when we get 0 work, the same amount of energy that's being put into the object is being taken out. That's one thing that's going on. There might not be any displacement. That might be another thing. Or no energy is being taken out or being put in at all, right? It might just be sitting still. So depends on what it is. That's what displacement means, right? No energy being taken out or put in. So you can have the same amount of energy being taken out as being put in, as being put into the object if you're moving it. Or if you have no displacement, right? No displacement or no displacement, no energy is being taken out or being put into the object. All right, so these signs are important, remember, because they're scalar values, all right? So that means positive means more than 0, negative means less than 0. So if we asked you to rank works, positive work is the largest, 0 work is the next largest, and negative work would be the smallest, because negative means less than 0 for scalars, positive sign means above 0 for scalars. Remember, these aren't vectors or scalars, and that's what that means, right? All right, next thing to remember, if you have no net force, you have no net work. So when do you have net force? When you're speeding up, slowing down, or changing direction. So if you're not speeding up, you're not slowing down, or you're not changing direction, you don't have any net work on the object because you have no net force. It takes net force to have net work, okay? It's an easy trick. It helps you to solve for things. So if things are moving at constant velocity, there's no net force, no net work. That's simple, all right? Just don't forget, cosine theta gets you the sign for work, okay? And that work's a scalar value. Make sure you're writing all this down. Remember, just watching doesn't do anything for you if you're not writing things down. Every one of these videos, you need to be writing everything down and then studying it and making sure that you can recall it all. This isn't just to watch. Physics isn't something to watch. Remember the saying in physics, if you can't it's easy to watch someone to come up with the logic. It's hard to come up with it on your own. It's a science. If you don't know these definitions and this understanding, this class will be hard for you, okay? Because you need to know. All right. Hopefully this isn't blocking that. I just realized the chair was there. I don't think so. So the next thing that we see is that work, right, is actually also, we can look at work, when we're doing work, how it can be associated with our motion, right? So when we look at net work, right, we know that there's a net amount of energy being put in to the object if we're speeding up in a certain direction. So let's take this example of a box being pushed, like this chair being pushed, starting at rest, and starts to be pushed and it speeds up, right? So when it starts to speed up, it's because, right, there's net force. Keep in mind, when it starts to speed up, when we talk about in terms of Newton's third law, right? Newton's third law, the push from my hand to the chair is equal and opposite, but the reason why the chair is starting to speed up is because of the net force. I'm putting more push, there's more force from the push, more newtons from the push than there is from friction, right? If I can overcome the amount of friction in the ground, the thing will start moving in the direction that I'm pushing it, right? Well, because of that, the thing that's important here, this is the thing to take away, is that force isn't a word that the universe wouldn't quite use.
The universe thinks of force as an exchange of energy and an exchange of momentum. That's why conservation of energy and conservation of momentum go together so well. And it's important to understand because they're trying to describe force. So yeah, we look at Newton's laws a lot because Newton's laws are about force, but really when you put force into an object, you're just putting energy into it, right? So when I push an object and it starts to speed up in that direction, yeah, I'm putting the net force, right? I'm putting more push into it than the friction, right? I'm also putting more energy into the object than friction's taking out if it starts to speed up, right? If I push it and it moves at a constant motion, that means that I'm pushing it, I'm putting the same amount of energy into it that friction's taking out, right? If I push on it for a little bit and let friction take over, friction was acting on that object longer than I was, so I put energy into it, but friction took more energy than I put into it, so it stopped. Okay, so force, right? This idea of force is actually just exchange of energy. We have to remember that, right? Because they all apply to Newton's laws, right? So we know that with net work, right? Net work is something speeding up in a certain direction. There's net force, and net force is equal to ma, right? So we can rewrite net work in terms of ma, all right? And when we do that, we kind of want to play with it a little bit because we're trying to see how net work fits into our motion. So the next thing we do is we look at the average acceleration. Now this is important. Okay, the reason why I'm showing you this derivation, you might not see it in class, this is how you would get kinetic energy, is because you have to know we're still talking about acceleration. Remember, acceleration is the most important thing in physics. If you don't know about it, if you're not interested in it, you don't know how to study physics because it's the change in motion. We're trying to study motion, so it's the most important thing. Well, with work, we use the average acceleration. So there's three ways to write average acceleration, right? I can add two acceleration values together and divide them by 2, or add 3 acceleration values and then divide them by 3, right? Or if I'm just using this simple one, a1 plus a2 over 2, I can also write that just as sum, right? When a1 plus a2 comes together, it's just going to be equal to sum a. So I can also write that as a over 2, or I can write that because a over 2 is also just 1/2 times a. Right? So there's a lot of ways to write average acceleration, but the point is that's what we use in here to start to look at motion. So why is that important? That means that because up to this point, kinematics was the only way to solve for how fast something went, how far something went, right? But that's not true anymore. We can do that now with this, right? With this new idea, right? But acceleration doesn't have to be constant. Remember, with kinematics, acceleration had to be constant to use those equations. Here, we're using the average acceleration to derive kinetic energy, so acceleration doesn't have to be constant. It can be constant and we can use this, but if it's not constant, it doesn't matter anyway because we're still just using the average. Does that make sense? So work, right? Work and kinetic energy, putting these things together, we'll talk about it over here, lets us solve for displacement of an object or how fast it's going. It's another way to do it, but when acceleration is a constant. So lets us solve for speed and displacement, no matter whether acceleration is constant or not, right? So when we sub in the average acceleration here, right, we just talked about why we're doing that, right? I pull the 1/2, I'm using this 1/2 times a, I just pull it out here, but there's the a, 1/2 times a, it's still that. I know it looks weird, but we do that for a reason, okay? Then we know a, acceleration is equal to change in velocity over t. So I change that a to change in velocity over t, so 1/2 m, that acceleration change of velocity over t, and that displacement stayed put. Well, that t is divided by all these, right? That's v over t. That t is divided by all these values. So I just want to move the t under x. And we know displacement over t is velocity. So I switch that displacement over t into velocity. So now I have 1/2 mass times velocity, or velocity times velocity is velocity squared. So we see work net is equal to 1/2 mv squared, which is kinetic energy. Okay, so watch this, go back, zoom in on it, whatever you need to do, but see what I'm doing over here to understand that work just isn't magically equal to kinetic energy. We just say work's equal to change in kinetic energy. No, we prove all these things. We can prove this too. I don't prove it on here, but we can prove this too. I prove it on a different video. But we can prove that work's equal to the negative change in potential energy too, okay? But it's not just made up. It's not something we're just saying, okay? It's proved, and we proved it. We got there using other physics, right? Using the things we knew about physics. We proved that F net times displacement cosine theta can also be equal to 1/2 mv squared. They're the same equation,
Okay, here's kinetic energy 1. Here's the original one we started with. But they're the same. Okay, they're saying the same thing. All right, so they can be equal to themselves, and that's what we kind of do over here. So that's looking at work. Now let's look at the conservation of energy, right? So the universe is essentially a giant bubble. So all energy is conserved because we all sit inside this bubble. So all the energy is essentially being used for work. Remember, when we say works, all energy is conserved, that means that all the energy is being used to do work. And what does work mean? Work means transfer energy, right? So that means that in terms of conservation of energy, all the energy is being used to do work in the universe. That's what that means. If all the energy is being conserved, it's all being used to do work. All right, does that make sense? So right now I can walk and I can rub my feet and friction's there and there's heat lost from my feet, right, to just the air, right, which means all the energy from me to the floor or from my motion, right, all the energy isn't being conserved into work, which means it's not all being transferred into me, right, or being pulled out of me, right? Friction isn't pulling all the energy out of me. Some of it's being used for heat. Does that make sense? And that heat just goes into the air. But if I were to cover me with a glass tube or something and rub my feet, that tube would start to heat up and I would start to absorb that thermal energy and I would start to heat up. So it would be then used to do work because work's just a transfer of energy. So if that glass tube starts to heat up and I start to warm up, that energy is being transferred back into me. That heat that's being generated from my friction, since I'm in this enclosed tube, I'm reabsorbing that, so now I'm doing work. It's just a transfer of energy, right? That's what work means. So energy can always be conserved just as long as we put it in a container. Does that make sense? And so that's the idea. The universe sits in essentially a giant container, so all energy at the end of the day is conserved, but it depends on how you look at the system. Sometimes it's not. If someone's just walking around and there's friction or something and they're not enclosed in a tube, well, that energy is just being lost. It's not conserved, right? But when all energy is conserved, the total change of the energy, right? Because energy is conserved back and forth from potential energy to kinetic energy, potential energy back to kinetic energy. That total change will be equal to 0. That's the idea of conservation of energy, right? So the total change in energy will be equal to 0, where that change in energy is always equal to the change in kinetic energy and the change in potential energy, or that back and forth. Because kinetic energy, right? I give this marker potential energy and I let go of it, it gets kinetic energy, right? Potential energy, kinetic energy. There's a constant conversion back and forth. And if that conversion is 100%, then the change between those, the exchange from kinetic into potential, will be 0. And that's what this is saying, okay? So, because of all these things we said, let's just kind of talk about some stuff. Because work's equal to the change, right? We know that the change in energy is equal to the change in K plus change in U. We also know the change in energy is equal to the net work. How much work is being done? Okay, we also know that the net work is equal to the change in kinetic energy, and the net work is equal to the negative change in potential energy, okay? We also know that net work can be equal to force, how far that force is being applied for, right? So it's important, we see all these things, right? We also know, yes, individual works can be equal to the individual force and how long they're applied, but work net can be equal to quite a bit of things, right? The total change in the energy of the system, the total change in kinetic energy, the total change in U. And keep in mind, because of this, we can write combinations. We can say change in E is just equal to the change in K if we wanted to. We could say the change in E is just equal to the change in U if we wanted to. Okay, because all these are equal to themselves, so they can all be equal. We can make fx cosine theta equal to both these, which is what we do. Okay, so just keep that in mind, because all these combinations, work can kind of be interchanged, all right? And make sure you also understand the different types of energy, all right? So kinetic energy is going to be the only energy related to our movement. So if we're moving, you have kinetic energy. If you just think of that, and it'll be in your equation, okay? If you're not moving, there's no kinetic energy, so it won't be in your equation. That's how that comes into play. So if you're moving, you have it, all right? The definition of kinetic energy is how much energy it takes to stop you, but we want you to know that it's the energy related to movement. So if you're moving, you have kinetic energy, okay? Gravitational potential energy is the energy stored. Remember, potential energy, all these U's are stored energy, right? So all these are going to start with stored. Gravitational potential energy is the stored energy due to height displacement, right? So I have gravitational potential energy because I was on the table. Now I've reached a certain height,
right? And so my gravitational potential energy is equal to this height, right? If I move the marker and instead of being over the table, now I'm over the floor, my gravitational potential energy changed even though I didn't move my hand, because it has to do with the displacement that the marker is going to go through, okay? So this is stored energy due to displacement. It has that much potential energy. When I lift it that high, that's how much potential energy it has, and it all will get converted into kinetic energy, okay? But gravitational potential energy you have, if you have some height displacement, okay, from some reference point, like the table's a reference point, so now I have height displacement, I have gravitational potential energy, all right? Elastic potential energy, all right. Now people think just because I'm attached to a spring or a rubber something, a bungee cord or something, I have this. No, they have to be stretched. So even though you're bungee jumping, you might jump off, and do bungee jumping until the bungee jump starts to, or until the bungee cord starts to stretch, you don't have elastic potential energy, okay? But once it starts to stretch, then you have potential energy, because elastic potential energy is the amount of energy stored due to stretch. Spring stretch, so when you stretch a spring, it's the amount of energy stored when the spring stretch, amount of energy stored when in a rubber band or a bungee cord, or even like bones and stuff. Bones are stretchy, right? They have give, they have elasticity. So when they're stretching, right? When you're laying down, you're not putting any, compression on them. But when you stand up, the bones have to stretch a little. They compress a little bit, and they get elastic potential energy because they're stretched or compressed, right? We think stretch, but remember, springs can also be compressed. So stretch or compress, the energy stored with that. This one you may use, you may not, but it's more related to like Kepler's law, but it's the amount of energy stored between two large masses that are interacting, like the sun and the earth, moon and the earth, those types of things. It's the amount of energy stored between those two objects, all right? And then this is the amount of energy stored in a fluid at a certain height. So let's say I have a pipe running, and then that pipe comes up to the second floor. Well, now that fluid has potential energy, because when it falls down, it's going to all convert to kinetic energy, right? It's going to get velocity because of its height, and that will be described this way, right? From the density of the fluid, the gravity, and again, its height displacement. Okay, so this is stored energy due to height displacement for the fluid. So those are the different energies that can always fit inside any change in U. So this could be change in elastic potential energy, where it's the final elastic potential energy minus the initial elastic potential energy. Maybe it's gravitational, okay? Kinetic energy, 1/2 mv squared will be in here, 1/2 mv squared will be in here, okay? So these can all interchange in here, but not also there, also down here, right? So when we start to derive the equation for conservation of energy, we start here where we say the change in E is equal to 0 and the change in Z is equal to, or change in E is equal to change in K plus change in U, right? So when we put those together, I should have written that probably before this, but we see 0 is equal to the change in K plus change in U, which is a really important equation. In fact, let me write that a little bit bigger, because this is the conservation of energy equation, okay? But then what we do is we bring U over to the other side and we get this equation, right? But you start with this, because that's conservation of energy. The total change in energy is equal to 0. It's just making these two equations equal to themselves. And then what we do is we want to see the relationship that kinetic energy and potential energy have to each other. So we try to solve for them. So the first thing we do is we bring the potential energy over. So we subtract it over. So it becomes change in kinetic energy minus change in potential energy, okay? You'll be asking, why did you subtract U over and not K? Well, we also know work's equal to the negative change in U, and work net's equal to the change in K. So if I make these two equations work equal to each other, I get the same one, right? So it's a fundamental thing that we want to have in our head to kind of think of it that way. And then when we expand this out, change in K is equal to final minus initial, change in U is final minus initial, but since it's a negative, the signs flip, right? So it's a negative, this turns into a negative, that turns into a positive, right? It doesn't in here because that's just the change, but since it became negative when we subtracted it over, all those signs change. And then what we do is we combine initials and finals together because we're trying to see the relationship between the initial energies and the final energies and how they're converting back and forth, and we get this equation. So this is the basic conservation of energy equation, where the initial kinetic energy plus the initial potential energy will be equal to the final kinetic energy plus the final potential energy. So these numbers will be equal. Whatever this number is over here, this number will be. Okay, keep that in mind. This is powerful and telling you a lot of things, right? But because of all the different kinetic energy, or well, the one kinetic energy, but different potential energies that we have, we can expand this out because it could be all the U initials, all the U finals, and the kinetic energies, which is what I did here. Okay, so most equation sheets don't have these equations on here that I'm giving you, but you need to know them, all right? So when we really expand this out and put as many, you'll really just have to worry about these three terms. Okay, these two are special cases that won't sit in here. So we want to make sure that these three terms are represented in here, right? So we have initial kinetic energy, initial gravitational potential energy, and initial elastic potential energy. And we can write it that way because this is just representing initial potential energy, initial kinetic energy, and it can keep expanding out based on how many potential energies we have in kinetic energies, right? And that'll be equal, right? This is equal to the finals, the final kinetic energy, the final potential energy, and the final elastic potential energy, right? Let's see, I don't have the F in there. All right, so this is really important. This is really important that you know this because you need to be able to use this. And then what you can say is like, hey, if I don't have a stretched spring, then this, right? Let's say someone's attached to a stretched spring, but it's not stretched yet. You don't have this in the beginning, but if it's stretched at the end, you have this, right? So you can eliminate that. You can always write this equation out for the problems that you need to solve, and then eliminate what you have. If the thing isn't moving at the beginning, then you have no initial kinetic energy. That would be 0 in this equation, right? And then, you know, based off what's left, you would have them. So I have other videos that are using this equation, know how to use it, but this is the one to know that you need to memorize it, right? Now, non-conservative forces, okay? Just like we were saying, friction, when there's no container over me, isn't being conserved. The energy isn't going to work. It's not being transferred to anything. It's just going into entropy, right? So non-conservative forces, right? How do we describe those? That's when all energy isn't being conserved. Well, we just use work now, right? When we know work is equal to the change in E, we know the change in E is equal to the change in K plus change in U, so we can write that equation. We put those two together to make that. And we know net work is obviously equal to this, so we have that. Since these are both equal to net work, we're going to make them equal to each other, which is what we do here, where this force is going to be any of the non-conservative forces, like friction or drag or something, right? That's usually where the non-conservative forces come from. All right, and they'll still be equal to the change in K plus change in U, all right? So I just showed an example. If it's friction, right, and that's the force of friction times displacement. That's just the sign, because friction will be opposite of your motion. So the cosine theta turned into that negative. The force is friction times displacement equal to the change in K plus change in U. Okay, so this is one, right? This is how we use that equation. Okay, this is how we use that equation to find non-conservative forces, and that's just an example, all right? And then I kind of just expanded it out for you a little bit more just generically, where it's force times displacement equals to the final initial kinetic energy minus the initial kinetic energy plus the final initial potential energy minus the initial potential energy, all right? Now keep in mind, like I said, because of this relationship, and I'll write it over here, right? Because we know that work, or because we have this equation down here, let's just ignore the potential energy for a second. We get this really cool equation where we can see that, and this is what I was telling you, that we have, and again, we can just do this because work's equal to change in K, right? And work's equal to this. So that's kind of what I'm doing right here, is just making these two equal to each other. That we have an equation, right? That's telling us displacement and speed, right? This is speed. This is speed. That's initial speed, final speed. And this is displacement. So now we have another way to solve for displacement and speed, right? With this new equation. That's another thing to know. It's not just for non-conservative forces. This is valid for anything. Conservative or not, you can use this equation to solve for this. Because if this is F net, I probably should have written this better. Because it should be F net, right? We can get the net force. If that's F net, then this displacement will be the total displacement of the object. Okay? So we know that this displacement we'll be solving for will be the displacement of the object.
if that's F net, because that's the total force that was applied to the object, right? So make sure you write it like this, because this is the one getting you displacement and speed, another way to solve for it, besides kinematics, right? This is easier to use in kinematics because there's no vectors in there. So that's what's important to pay attention to. Now just this last thing, just remember power, right, is the rate at which energy is pulled out of an object, okay? Right, it's also the rate of work being done, which is the transfer to or from an object, or the rate of conversion from potential to kinetic energy, all right? That's all power is. So power is the rate of work. This is how we start it, right, which is work over time. Any value over time is a rate, right? This is work over time, right, net work over time. We know network's equal to change in E, so that means because of all this, we can write this a lot of different ways, and that's all I'm doing over here. Okay, I'm not doing anything special. I'm just because we know work net's equal to all this stuff, power can be written a lot of different ways. All right, so work net, right, we can write power as the change in E over time. We can write power as the force times displacement cosine theta over time. But if you do that, remember x over t is velocity, so it would be force times velocity cosine theta. And typically this cosine theta drops off, so it's just force times velocity. It's another way to find power, right, because of our combinations here. Another way to write power is the change in k over time. Another way to write power is the negative change in u over time, right? So all these different combinations, but if you need to know power, the rate at which energy is pulled out, or the rate of work, what's the rate of work being done, that's how you do it, all right? I hope this was helpful. Again, these are the concepts. You need to know these. You need to write all this down. Everything that's on the board you need to know, have written down and be in your head for the test, all right? I'm super proud of you. So keep up the good work, and I'll see you on the next video.